We'll talk about the environmental considerations of PV power plants right away. When we use PV power plants, do we get any emission into the atmosphere? What are the impacts on the environment where the PV is installed when we use PV power plants? Again, another aspect of the environmental factors or aspects of PV power plants that is not popularly looked at is the aspect that has to do with the manufacturing of a PV power plant. Okay, in manufacturing PV power plants, how much emission do we have in the atmosphere, or do we, put into the atmosphere? All of these we are going to look at in this course, and then we're going to try to weigh it against the economic implications. We're going to try to weigh it against the technical aspects of PV power plants. Okay, so let's go ahead. The first question you probably want to ask yourself is, why look at the environmental considerations at all? What is the importance and benefit of looking at the environmental considerations of PV power plants? The most important reasons for looking at solar as an alternative source of energy are listed below. The first one is to harness clean energy from the sun. Over the years, it's been a priority for several policymakers, for several nations, to harness clean energy, to have clean energy in the sense that we have less emission, less pollution, less gases in the atmosphere that could actually endanger the living organisms' lives. So we need to access clean energy generally. Okay, so that has been a concern of the entire world, the policymakers, and so on and so forth. So one of the things that the PV system produces, one of the advantages it produces, is that it helps us to harness clean energy from the sun without necessarily putting all of these emissions into the atmosphere. Again, to mitigate the energy shortage in the world in a cleaner way. So this is the second reason we need to patronize PV power systems as an alternative source of energy. So we should ensure that the process of building PV generators and the systems doesn't undo the good that they do in their usable lifetimes. So this is where the clause comes in. It is okay that the PV power plant would actually generate power, they will generate energy, and they will not emit gases into the atmosphere. But then, what about the gases that have been emitted into the atmosphere while we were trying to produce the PV modules, while we were trying to produce the PV module devices, the balance of system, and every other thing that is connected to the PV power plant? All of these things require energy to produce them. Even the PV itself requires a lot of energy to produce it. So while trying to produce the PV, we are trying to produce something that will give us energy, but we have to use energy from what we are trying to eliminate to produce what will help us eliminate it. So from there, you begin to see that we need to do more, about understanding the dynamics between the environmental effects of PV power plants. Let's take it a step further from here. So, how do we quantify the environmental impact of PV systems? How do we measure if they are having a positive impact in their lifetimes, be it 20 years, 25 years, or 30 years? Number one, it is important that you pay attention to this. So let's look at this. Number one, measure the carbon footprint of the carbon emissions caused due to the manufacturing of PV, and then compare with the carbon emissions offset by the panels during their lifetimes. So this tells us that during the manufacturing of the PV, there are high possibilities that some emissions occur, are ejected into the atmosphere. So we have to measure that carbon footprint during the manufacturing of PV panels. We have to measure the carbon footprint of carbon emissions that are caused during the manufacturing of the PV panels, and compare with the carbon emissions offset by the panels during their lifetime. So this is important. This is one of the ways where you can measure the environmental impact of PVs over their lifetime. Number two, an analytical approach is to look at the total energy spent in the manufacturing of various PV panels or systems. Different manufacturing processes have different energy needs, and these are then compared with the clean energy produced by the PV systems over their lifetimes. In the first one, we are paying attention to carbon emissions when manufacturing the PV modules and comparing it with carbon emissions, or comparing them with carbon emissions during the lifetimes of the PV systems, during their lifetime, during operations at their lifetimes. Now, in the second part, what we are looking at is the total energy spent. Now, we're not looking at the carbon footprint. We are looking at the total energy spent in manufacturing of the various PV panels or systems. How much energy did we use to provide the PV system or PV panels? Then how much energy will the PV system produce in their lifetime? And then we compare these two energies together and then see which one is higher, which one is better at the end of the day. This is another way of comparing the environmental effects of PV, of measuring the environmental effects of PV panels. Then number 3 is to do a complete life cycle analysis. This is key. Do a complete life cycle analysis, trying to trace energy and carbon footprint. Okay, the first one is just carbon footprint. The second one is just energy. And the third one is a holistical approach that combines the first and the second. Okay, it combines the energy and the carbon footprint of the PV panels throughout their lives, from cradle to grave. Okay, that's what we refer to as throughout their lives. Okay, so the third method combines both the first and the second method. So these are 3 ways by which we can quantify environmental impact of PV systems globally. All right, let's take it a step further. Now let us look at the energy-based approach. We talked about the carbon footprint approach. We talked about the energy-based approach, and then we talked about the approach that combines both of them together. So let us look at the energy-based approach now. In this particular teaching, for your level and for this particular class, we are going to focus more on the energy-based approach. Some basic terms related to today's approach are the energy yield ratio and the energy payback time. Now, this is not the economic payback time. This is energy payback time, and then we have the energy yield ratio. So the energy yield ratio, it's a ratio of the total amount of energy yield of the PV system to the total amount of energy invested in its lifetime. This is very important. So when the PV system is operating, how much energy will the PV system yield over its lifetime? And then what is the total amount of energy invested in the PV system over its lifetime? So mathematically speaking, energy yield ratio is equal to energy yield of the PV system divided by energy invested in the lifetime of the PV system. This is a simple mathematical expression that you should try to remember and then understand its applications. Okay, let's go on. The PV yield depends on several factors. We've mentioned some of these factors earlier. It depends on the site of the PV system, the quality of the panels, and then the technology choice. Different technologies have different efficiencies. Different panels have different quality because they've been provided and manufactured by different manufacturers under different circumstances. So their qualities are actually not the same. Their qualities are not the same, they differ. And then the site of the PV system, we've mentioned this over and over, because a site that has more sun will give us more energy, will give us lower LCOE and more energy, and so on and so forth. Okay, so we have to know that the PV yield depends on these 3 factors. It is therefore possible to see a wide range of energy yield ratios when observed in practice because of variations in these factors that affect the PV yield. PV modules can have this ratio as large as 10 to 15. This ratio can be as large as 10 to 15, while PV systems will usually have smaller energy yield ratios. Here we're focusing on the modules now, and then we're also focusing on the systems. The modules have the energy yield ratio larger or higher than the energy yield ratio of the entire PV system. All right, just as the efficiency of a module will be more than the efficiency of the entire system by virtue of some losses along the line. This is very important. What is energy payback time? We've talked about the energy yield ratio. Now, what is the energy payback time? This is defined as the total energy input over the lifetime of PV system to the annual energy yield of the system. So systems economic payback period and energy payback time are not the same. They're entirely different. So the energy payback period of most systems is somewhere between 1 to 7 years. This is energy payback time, depending on the equivalent on hours available in the place of implementation. So energy payback time is calculated using this particular formula, which is total energy input divided by annual energy yield. Total energy input divided by annual energy yield. So here, we are going to quickly talk about the amount of energy required in PV manufacturing. These are different technologies. These are different module technologies, as you can see here. And then some of these module technologies are displayed alone, displayed with frame, okay? And then they are also displayed with minimum values and maximum values. So you can see for each of the graphs, you will see 4 things, 4 interpretations, 4 measurements for each of the graph. For example, this particular graph, this blue light, this particular one that stops somewhere here, talks about the CIGS. This is copper, indium, gallium selenide. The CIGS with frame, this is the amount of energy, minimum amount of energy that will be needed. It stops here. The CIGS with frame. So this is the minimum amount of energy that will be required for the manufacturing, all right? And then the maximum with frame will be the one with this thick blue, okay? This one here. So this tells us that when we are producing CIGS modules without frame, we will spend less amount of energy compared with when we add frame to it. So the adding of frame to it would also consume some amount of energy, which is accounted for here. Again, for the second part, you will see the CIGS without frame now. Without frame, this is where you have, this is without frame, this is where we have in terms of energy investment. Then without frame, maximum is going to be here. So without frame, this is the minimum value we can get here. And then without frame, maximum, this is exactly what we can get. With minimum, this is where we can get. With maximum, this is where we can get. Okay, so there is an account for the maximum value and then the minimum value. So you will see that the value ranges from a particular value to another value. With frame, we have the minimum and maximum. Without frame, we have the minimum and the maximum. Okay, so you will see that with frame, if you trace it down, total amount of energy that we have with frame will come to somewhere here. Without frame, it will come to somewhere here on the average. Okay, so you see the difference of amount of energy invested for copper, indium, gallium selenide, CIGS. So just the way I've explained this, you can look at the CDTE, the cadmium telluride modules. You can look at that and then see the energy, investment level. The same thing goes for the amorphous modules, polycrystalline modules, and the monocrystalline modules. What you will find out is that the maximum and the minimum for monocrystalline modules, the maximum and minimum for with frame investment is highest in monocrystalline modules. Okay, this is it here. You can see it here. So you will find out that monocrystalline with frame has more energy consumption, has more energy investment than all the other technologies. Again, the difference between minimum value for with frame and maximum value for with frame for the monocrystalline is high. Same thing goes for a minimum value without frame and maximum value without frame for monocrystalline modules. You can see the disparity, the variance of the difference is actually very high. Again, monocrystalline consumes more energy than all other technologies when it comes to energy investment in creating and producing them. And then follows by polycrystalline modules. So all crystalline modules are actually consuming more energy, then followed by amorphous, then followed by the CIGS, and then followed by the cadmium telluride. The cadmium telluride is consuming the least amount of energy when it comes to production and manufacturing of the modules. Okay. Thin film technologies like amorphous silicon cost much less energy to produce to be produced compared to the monocrystalline silicon, which can easily consume around 12,000 to 18,000 kilowatt hour per kilowatt peak for production. You can see that. So 12,000 to 18,000, that's some amount, that's huge, basically. Numbers are often changing and would only read better as the manufacturing technology improves and the processes become more energy efficient. So what we want to focus on here is the processes for producing the PV modules. We have to find a way to make sure that these processes don't consume too much energy. This is key. This is very important. We have to find a way to make sure that these processes don't consume too much energy. And that means as the time rolls by, we should improve in our processes, okay? Energy spent in the manufacture of PV, of the entire PV system, would be more than that required for the PV module, because for the entire PV system, many more devices would be included, okay? So it certainly would have more energy consumption than energy consumption we experience when trying to produce or manufacture the PV modules. It is difficult to allocate the exact energy costs to balance of system components like batteries and inverters, and mainly because the technologies and manufacturing processes for balance of system might vary a lot across variety of products and products that are available in the market. So, but then with them in play, the system would have more energy consumption when producing them than the energy consumption we experience when producing just the modules alone. Okay, let's go forward. Here is a graph that talks about the amount of energy required in PV manufacturing by comparing some of these modules together. And then we're going to look at the energy payback time to explain in detail some of these analyses. In general, energy need for the balance of system is significantly lesser compared to the PV module manufacturing. We talked about that already, depending on the PV technology and then the balance of system. So we talked about this already. Look at the energy payback time for the module frame, and then for the balance of system. We're going to check all of those together, and then we would look at the energy payback time majorly. We would look at the energy payback time in years for, we will compare crystalline silicon with amorphous silicon here for this particular graph. Crystalline silicon and amorphous silicon, we will compare those for those two module technologies for this particular graph, and we are going to be focusing on their mounting techniques. There are different mounting techniques for PV power plants. We have the roof mount, we have the ground mount. So this graph also focuses on just two types of mounting techniques, the roof mounting technique and then the ground mounting technique. And then the third thing we want to look at here, apart from looking at the two types of technologies we have, two types of mounting technologies we have, we want to look at a scenario where we have high solar, high irradiation, medium irradiation, and low irradiation. We want to look at the solar irradiation level. This talks about the site, the location where the PV systems are being installed. So this blue color represents the module, the orange color represents the module frame, and then the green color represents the balance of system. So you will be able to see the energy payback time for each of these segments, all right? And then you will be able to see the energy payback time for each of the main systems, considering all the parameters of analysis that we are paying attention to. So for high irradiation, we would compare both roof and ground, and then crystalline silicon and amorphous silicon. So let's compare the roof mounted system and the ground mounted system. You will see for high solar radiation, the energy payback time for the ground mounted system is more. So that simply means that we are going to be investing more energy for the ground installation, and then it will take us more time to get our energy that we invested back for ground installation compared to the roof installation. So that is the mounting techniques comparison. Then let us look at the technology comparison. When you look at the crystalline silicon and amorphous silicon on the roof, you will find out that crystalline silicon has higher energy payback time. That simply means that it has, you will pay for the energy using more time than using more time in crystalline silicon than the amorphous silicon on the roof. The same trend is also seen when you look at the ground analysis, okay? For crystalline silicon, you know, the energy payback time is higher than the amorphous silicon. Don't forget, when we started, we said that the energy payback time is defined as the total energy input divided by the annual energy yield. Total energy input divided by the annual energy yield. That is our energy payback time definition. All right. So for high solar radiation, this is what we have. And by high solar radiation, we're referring to something as high as 2,200 kilowatt hour per square meters per year. So you can see we have the medium radiation, and then we have the low radiation scenario. So what you can observe here is that when we have low radiation, when the solar radiation is very, very low, it simply means that we are producing less energy, and then the energy payback time is going to be way, way higher for all the scenarios being examined. All right. The same thing goes with the medium radiation. So with the higher radiation, you will find out that we are experiencing lower energy payback time compared to the medium, you know, solar radiation season and high and low solar radiation section. All right, this is important for you guys. So I've been able to break down this particular graph I've been able to analyze this graph for you guys. There are about 6 or 8 more graphs like this, considering different scenarios. So I'm not going to explain each of the graphs. You are going to have to go through each of the graphs yourself, but I wanted to make sure that you understand this first one. That's why I've taken my time to break it down into pieces for you. For the medium irradiation, you will find out that for the ground-mounted system, the payback period is even higher than the roof-mounted system. So when the energy payback period is low, it's better than when the energy payback period time is high. Okay? When the energy payback period is low, it is better than when the energy payback period time is high. So that is why we said that energy payback time is equal to total energy input divided by annual energy yield. Okay, so when the energy payback period is low, it simply means that the annual energy yield is more. Okay, when the energy payback time is low, it means the annual energy yield is more. That's what it simply means. Okay, let's go on. All right, so I want to assume and believe that you all understand exactly what this graph means, and we can move on to the next slide. Let me clean this up a little bit. So you can see various levels of comparison. We compare 2 mounting techniques, 2 different technologies, high radiation, medium radiation, and low radiation scenarios. And then you can see that we focus on both the module frame, and then the balance of systems. This particular graph is talking about the irradiation, okay, solar radiation. So regions of higher irradiation shows lesser energy payback time than PV systems in low irradiance areas. We talked about this already too. It can be seen that the module's energy payback time is smaller than that of the entire system. You can see that already. So when you look at here, where is the module is blue, all right? So module energy payback time, this is module energy payback time in blue here. For all the systems, for all the configurations we have, the blue will be the module energy payback time, and then the entire system is putting all of them together. So you will measure here that module payback time is smaller than the entire system for all of the configurations that we have. Okay, in this particular case, it is even way smaller in this particular case. All right, thin film amorphous technology-based PV panels may pay themselves back faster in terms of energy due to their lower energy manufacturing processes. So these are very important points you have to pay attention to. When you compare crystalline silicon and amorphous silicon, you find out that amorphous silicon has lower payback time here. It also has lower payback time here. Okay, it also has lower payback time here. When you compare amorphous to crystalline silicon, here is the only place where you have, the crystalline and amorphous having the same payback time for the system. But in terms of module, amorphous still has lower payback time, all right, than crystalline silicon. In this particular case, the same scenario, Here again, they are almost the same, but then the module has lower payback time for amorphous. The reason for this is that the energy invested in producing amorphous silicon, like we explained in the previous teachings, is way lower than the energy invested in producing the crystalline silicon modules. And then, of course, the entire system. Okay. In general, the energy payback time across technology and irradiance levels is seen to be between 2 to 6 years. In any case, the maximum is going to be about 7 years. The balance of system for PV systems based on the same technology have a larger payback time owing to the lower yield of the amorphous silicon panels. Okay, you can also see that when you look at, you can also see that when you observe and monitor the graphs properly. Okay, now we can talk about the amount of energy required in PV manufacturing. The thin film amorphous silicon panels can work better under diffused light. The crystalline silicon panels are more efficient, but amorphous silicon panels are less power intensive while manufacturing. A lot of optimization is required at the system level to choose the optimal module depending on several factors. Energy payback time is much lesser than the PV module's lifetimes, which can be as high as 25 to 30 years. We've talked about this before. Okay, so you need to pay attention to some of the points that are raised here in terms of diffuse light. Thin film thrive better under diffuse light. Crystalline silicon panels, they are more efficient. Amorphous silicon panels, they are less power intensive when manufacturing them. These are 3 characteristics already mentioned in these 2 points. And then you need to be able to know which one is which when you're looking at them, okay? For the systems discussed in the previous graphs that we checked out, the energy yield ratio are also anywhere between 4 and 10. It means the energy invested in the PV system manufacture is paid back several times over during its lifetime, all right? For example, if the PV system has energy payback time of, let's say, 4, or any number between 4 and 10 is 5, all right? And then the lifetime of the PV system is actually usually 25 to 30. Let's pick 30. So, or probably we can even pick 25. If you pick 25, what this simply means is that after the first 5 years, we would have paid back the energy used in, we would have had the energy payback time in the first 5 years. Okay, the energy used and invested in producing the system will have been paid back within the first 5 years. So that simply means this energy can be paid back how many times? 25 or 5. This energy can be paid back 5 times in its lifetime. That energy used in producing can be paid back 5 times in its lifetime. If we pick 30 as the lifespan of the PV system, it means that 30 divided by 5 will give us 6. And that would mean that the energy payback time can be paid back 6 times during the lifetime of the PV system. Okay. So we can conclusively debunk the myth that solar panels consume more energy to be produced than they generate throughout their lifetimes. There's been a lot of discussion about the fact that the energy that we spend in producing PV systems is usually more than the energy that we generate with the PV systems. From this analysis, from this explanation, from what we have seen so far, we would be able to see theoretically that the amount of energy spent or invested in producing a PV module or a PV system is way below the amount of energy generated by the PV system over its lifetime. Many times 5 times more or even 6 times more along the line. So the EU already has in place several recycling directives that have led to recycled practices in place for the large amount of crystalline silicon panels being used. Okay, recycling simply means that when a PV lifetime is over in 25 years or 30 years, the PV can be recycled and then it can be used again for another 5 to 10 years or 15 years or even around somewhere around there. So there are studies that indicate up to 80% reduction in the production energy of a panel. So when you recycle PV panels or PV modules, the amount of energy production could just be 20% or just around 20%. So there will be 80% reduction. This would further reduce the energy payback times of the crystalline silicon panels. Thus, it can be said that PV systems are beyond doubt net energy positive in their lifetime, because after their lifetime, you can still use them again, okay, and then you generate more energy after you use them, okay. So when you recycle PV modules, these are some PV modules that you can recycle, and then the percentage that can be recycled. So for 100% PV modules that you use for 30 years, and then you want to recycle, for crystalline, you can recycle 80% of crystalline PV module. You can recycle 20%, almost 20% of CIGS module. For cadmium telluride, you can't recycle them at all. And then for flexible modules, other flexible thin film modules, you can recycle probably less than 5% or less than 4% of the original PV module. Okay, this brings us to the end of environmental considerations of PV modules.